Hi there, I'm Alina from Iceland Review, and we are back at the eruption site, or like, it's not erupting anymore. We are standing on one of the berms in between the crater, which is right behind me, and the power plant and the Blue Lagoon. So in this week's video, you can watch part 2 of our interview with our expert, Þorvaldur Þórðarson. I recently read a report from the Earth Science Institute at the University of Iceland that the lava composition of this current eruption is different than from the earlier compositions of the series. And it resembles more the 2021 Geldingadalur lava
the
composition.
very beginning of the 2021 Geldingadalur eruption.
Okay.
Not the whole thing. So
Okay.
the magma that was erupted in form of tephra and lava in the first 17 days of the 2021 eruption is different from what came after.
Okay.
And they're significantly different. And we've looked at that in quite detail, and all the evidence that we have, both the chemical composition and other signals in there, which are indicating that this magma was actually contaminated by the crustal envelope that surrounds the conduit, and also is probably old magma that actually has been residing down in the magma storage zone, the deeper magma storage zone, since the last eruption period 800 years ago.
Okay, so can I imagine it as some kind of plug? Like it's an old surface, and that's what came up first?
Yes, so it is very interesting, because we know that the deeper magma storage zone that fed most of these events that we've been experiencing on the Reykjanes Peninsula was formed somewhere between 2002 and 2020, and most likely in the period of between sort of 2016 to 2020. And formed is maybe not the right word. It started this fresh magma started to accumulate in a magma storage zone at 9 to 12 kilometers depth in that time period.
Okay. And
then when you had accumulated enough magma there, then you pressurized the system enough, and then the opening, the tectonic activity, the earthquakes, created a situation where that magma can actually start move upwards towards the surface. And as it did that, it encountered this old magma which was sitting in this storage zone since 800 years ago.
Wow.
And so this new fresh magma sort of encountered this old magma and pushed it out ahead of itself to make ways for itself to get to the surface and erupt. So that's why we had this old magma coming out in the early days of the 21 eruption. And when it had pushed all that out, then it could come out itself. And you had this new fresh magma, which is, we call it enriched, because it has a slightly different chemical signatures than the old magma. And that was kind of a nifty story in its own right.
Yeah. Now,
since then, we've had this new fresh magma being erupted in a number of eruptions, both in Fagradalsfjall, which is behind us over there, and also at Sundhnúkar, over here to the west. And until this eruption that started on the 29th of May, then suddenly we get magma with a similar composition, similar signature as the old magma that was erupted first. We haven't confirmed that it is the same magma, but that's something that would be interesting to try to confirm.
Okay, so that's being or you're
and that's
analyzing
why we want to go
now?
and sample those.
Yeah,
things.
yeah. Okay, so could it be just basically old layer again? But I mean,
if it is, yes, it could be.
Yeah.
The answer is yes.
Yeah.
And if it is, then that means that you have somehow stopped the new fresh magma to come up.
Okay.
You closed the pathway that it was using for that magma.
Yeah.
And that now that pathway has been filled by then the old magma.
Yeah.
And if that's the case, then I think we would think of it as you're shutting down this source of new fresh magma, making sure that it can't come to an eruption, and you're dragging out some of the old magma that has been there for a long time. And to me, that would signal that towards sort of the end of this unrest activity at Sundhnúkar.
Okay.
So if we're right, then this would be another signal that this unrest that we've been experiencing in the neighborhood of Grindavik might be coming towards an end.
Recently on Vísir, I think you said that the activity could end in late summer, around August. And is like the lava composition now that we're seeing one of the reasons why you stated this, or where is that coming from?
No, I didn't know about the lava composition when I actually said that.
Oh, yeah.
So that's a new evidence.
Yeah, okay, that could prove.
Yeah, and would be then additional evidence to the argument. But the argument was based on observation which not only me had made, but Haraldur Sigurdsson and Grímur. They had also made that observation and did similar kind of calculation. The numbers are slightly different, but that just reflects the uncertainty in those numbers. But the general conclusion is the same. So what we've been observing, and this comes from the Met Office data. Basically, if you look at the plots that the Met Office puts out, and they're showing a diagram where you have time on the x-axis and sort of the duration of inflation or rate of a magma accumulation on the not rate of magma, but just magma accumulation on the y-axis. So you get lines, and the slope of those lines is actually the rate of accumulation. So the steeper the slope is, the faster it's accumulating. And what the graph shows, and what's been happening with time, is that it was pretty steep to begin with, but it's getting flatter and flatter with time. And that means that the rate of inflation or the rate of magma accumulation into the shallow magma storage under Svartsengi is slowing down. In other words, the rate of magma flowing from the deeper magma storage zone at 9 to 12 kilometers up into the shallow storage zone at 4 to 5 kilometers is slowing down. And if that's slowing down, then if it continues to slow down, then it will actually reach zero by end of summer. And it could stop before that, because it's very hard to keep a conduit open when the flux or the flow is less than 2 cubic meters per second.
I read numbers that it's now about 4 to 6 cubic meters per second.
Yeah, it's probably less now. So it's probably between 3 and 4 cubic meters per second at the moment.
And was the maximum that then around December and around Christmas of the influx?
From the influx from the deeper as well was over 9 cubic meters per second.
9, okay.
So that's that's a change, and it might have in short period of time been even greater than that. This is sort of an average for the time of November, December time.
Okay. Does that also coincide with, I mean, now the eruptions have just gotten longer and longer. I mean, we don't know, the current one is still active and it hasn't surpassed I think 56 days of the
No, it's only 3 weeks.
Exactly. But it kind of seems like they could get longer and longer. Would that coincide with these findings?
No, that's an interesting development, and I don't know whether that is because the rate of flow is slowing down, or whether there's something else. So if you think of a deeper storage zone down here, and then you have some kind of a conduit that actually feeds from there into the shallow magma storage zone, and then you fill this shallow magma storage zone, and periodically you've been opening up another conduit all the way to the surface to produce the eruptions. Now, maybe it is that the opening into the shallow magma storage zone is got clogged or something, so part of what was coming from below just went straight up. That's a possibility. Or the other possibility is that these things are coming up, getting into the shallow magma storage zone, but it's difficult for it to get out of there, or the inflow is slightly greater than the outflow, and But what exactly the scenario is difficult to sort of state for certain right now.
Yeah.
But we do need to look at all the data that we have and see what scenario is going to be fit best to the actual data that we have.
Okay. I mean, now there's land rise at Svartsengi again, meaning
Yes.
that there's not basically enough being, spat out by the volcano. Then, so it equals
No,
out.
yeah. Some of the magma that is coming from the deeper storage zone is clearly not going all the way to the surface.
Yeah.
It's going and accumulating into that shallow storage zone. So, and that could be potentially explained that your inflow into that shallow storage zone is greater than the outflow.
Yeah.
So then you accumulate things and you have the inflation. But the inflation now is slower than it has ever been.
Okay, so it could also end up that this eruption will end, and then you called it the storage, this shallow storage.
Shallow magma storage.
Will just fill up, but it could be that it's not enough that it will
It might not reach that critical volume that it requires for it to open a new pathway or reopen the old pathway to the surface. And the fact that it is now filling in at a slower rate than it has ever been suggests that even if it will manage to fill everything up, it will take a longer time.
Okay. So last time the critical point was always at was it 13, 14 million cubic meters? Then last eruption was around 20, way more.
Yeah, so this one is now over 40.
Okay,
so maybe 40, maybe well, that's the bulk volume. Now and the bulk volume is around between 40 and 45 million cubic meters at the moment.
Yeah.
But you have to also remember 25% of that is just void space.
Okay.
So the true volume is probably closer to sort of 33 to 35 million cubic meters.
Basically the rest is just airspace.
Yes, it's just void space. And because lavas have bubbles in them and there was freeze in them.
Yeah.
And they also join spaces when they cool down and things like that. Yeah. Whereas the magma that is flowing down up through the conduit, it doesn't have any bubbles in it, and it's actually just very, it's a dense fluid.
Yeah.
And also the lava that flows through the transport system of these like the lava tubes or the lava channels, that's also under pressure, so it doesn't have any bubbles in it.
Ah, okay.
So, and if you want to calculate out the correct, magma discharge, what we call it, it's the flux or the flow rate, then you have to correct for the void space. You have to take the void space out.
Okay.
Otherwise, you give numbers which are too high, which in this case would be 25% too high.
Yeah.
And so you make the event more dramatic than it necessarily has to be.
Is there always, I'm just curious, an estimate of how much void space there is for all eruptions, or do you need to calculate that too?
It's a very approximate value, which is based on observation of old lava flows like this one. You can you see, if you look at this one, you can see there's a lot of void spaces in here, and you can see the cracks, for example.
Yeah.
There are cracks like that, and also in newly formed lava that is solidified.
Yeah.
And they take up space.
Yeah.
And all the bubbles that you see in the rock, all the little holes.
Yeah.
And so the range is anywhere from 10 up to 50%.
Wow.
Can be a void space.
Okay.
And it's not necessarily uniform throughout the lava either.
Yeah.
So there's more void spaces in the upper part, in the crust, and the top part which is cooled down.
And the lower part.
And the lower, it's a bit denser. So when you do these measurements and you go around and you measure a lot of old lava flows, you can estimate in a vertical section, you can estimate the amount of void space that is there, and then you can take an average of those measurements, and that's the value that we use when we're correcting in an active eruption, because we don't know what is in there.
Oh, that's very cool. Very interesting to know. So talking about you call it shallow magma storage space. Because I also heard it's not a chamber in Svartsengi yet. Apparently it can turn into a chamber. Can you tell me more about that? What's the difference between a magma chamber?
Can you tell me what is a chamber?
That's
all these terms, and they're just terms.
Okay.
And they people and we use them.
Yeah.
We should say the scientists, we use them to try to ease communication.
Yeah.
But if we start to have too complex of terminology or hang our hats too much onto the terminology, it just becomes confusing.
Okay.
So so magma chamber is basically thought to be some kind of a irregular body, bulbous body that actually is a storage zone for magmas.
Yeah.
And there is no specification of its size.
Okay.
No specification of its lifetime.
Okay.
Or anything. It's just, it's some kind of magma storage.
Okay.
So that's why I call it magma storage, because everyone understands. When I say it, this is where I store things.
Yeah.
That's a common language.
Yeah.
If you're communicating things to the general public, you want to try to keep the language as simple as possible.
Yeah, and that's also, I think, one of your fortes, to keep things simple, everybody understands.
Well,
and
otherwise it would be pointless.
Yeah, that's true.
If I sit here and talk about things and no one understands what I'm saying, then it's a waste of time, everybody's time.
Yeah.
And it's very easy to fall into that trap when you're talking about these things, because we are used to certain terms and certain terminology, and we learn those things, and we kind of sort of by time get used to using them, and we use them without thinking. And then you say all these things, and people around you just look at you and say, what is he talking about?
Just like lots of question marks.
Just like,
yeah, I mean, we can see right behind us is already a group going to, I guess, the old eruption site.
Yes, the Þórðardalsfjall eruption site, which is up that way.
Yeah, one big question on Facebook in these geology groups is, why can people not go close anymore? Meanwhile, the last 3 years, people could just hike up to the volcano. It was this kind of adventure thing. What changed now in this eruption? And also the last 5, of the series.
Okay, there are there are a few things that have changed.
Yeah.
Some of those changes are real physical changes to the nature of the eruptions. Especially the early stages of the eruption that have been happening on the Sundhnúkar lineament. There's really high flow rates at the beginning, or flux at the beginning. So, and in this last one, flow rate was on the order of 1,000 cubic meters per second, maybe a little bit more than that. And compared to when we had the one in Geldingadalir in 21, in the beginning, that was about 4 cubic meters per second.
Wow.
So there's a huge difference. And the faster the magma comes out of the vent, the higher the fountains are. And also when the fountain material comes to the ground, and also what wells out of the vent moves then faster away from the vent. So the lava flows are moving faster, and we have seen that. They've gone pretty fast. I mean, like some of the lavas in this recent event have been flowing at about 1 kilometer an hour. And in some instances locally, so in local places, they've actually been moving. When they break out, these sort of side breakouts from the lava, they move fast enough that you can't run away from it. So those who are in charge of making the hazard assessment and issuing the warnings and advising the authorities, I think rightly have made that call that these eruptions, at least in the beginning, are more dangerous.
Yeah.
Now, when they slow down, and the magma discharge is like it's right now, where it is significantly less, they're not as dangerous, and then they're about the same as what we had in Þórðardalsfjall.
Okay.
And then we can probably have a discussion and debate whether we should then open up access to these things. And I'm not quite 100% sure what goes into the argument, but I suspect that the proximity of the town and then also the power plant in that plays a role in the decisions made.
Yeah.
And I'm sure they have, reasonably good reasons for making those decisions. But I think it also should be at least explain publicly why.
Yeah, yeah.
I mean, that would be nice to get a public statement of why this is the way it is, not just we've closed.
Yeah.
So maybe we're lacking there in terms of explaining what are the reasons for the more restricted access now than was in terms of Þórðarfjall.
I mean, I could imagine that a lot of the workforce from search and rescue is now being used to just take care of the town and just the traffic in and out, and that they don't want to spend it on like...
Some of them are, but let's not forget, search and rescue are volunteers.
Exactly, yeah.
And even though they get paid a little bit, they have other jobs.
Yeah.
They need to attend to as well.
Yeah.
So it is important to take that into account when we're thinking about how available they are, and we can't operate these kind of things, on the basis of volunteers and goodwill of people. We have to, we have to think of new ways of doing it.
Yeah, yeah. I mean, I remember the last few eruptions. I think I've been to every single one besides the 2022 August one.
Mm-hmm.
And search and rescue were everywhere, and just always checking the gas levels and sending people away if they were too high, and it was incredible load of work.
And the gases are an issue, and depending on, of course, how much magma is coming out per unit time, because the gas flux is a function of that, and also the wind direction.
Yeah.
And so I mean it is a. Even though it doesn't maybe look dangerous, it is a dangerous place. And also when you are along the lava flows, I always was concerned about people's safety up in the eruption in Þórðarfjall when people were next to the margins of the lava, because you never know when you have a breakout from the side.
Yeah.
And those breakouts can move very fast, faster than you can run.
Yeah. And
if you happen to be in the wrong place at the wrong time, that's it.
It's over.
Yes, because that lava is 1100 degrees C. So.
Yeah, yeah. So talking about the pollution, what effect, that's a common question from many people, what effect does an active volcano have on the climate? Like with the pollution cloud and...
Well, I think it's better to think of it, what is the impact on the atmosphere?
Okay, yeah.
And because you have multiple impacts from eruptions on the atmosphere. So the fundamental one, which is quite obvious, especially when you're close to a volcano, is the pollution factor. So you have these toxic gases form some kind of a plume that has been moving. It moves away from the volcano. It might be up above you to begin with, and it moves away. It sinks down and it comes back in with the wind from the sea and things like that. And you have sulfuric acid in those plumes. You have, of course, SO2, chlorine, and fluorine as the primary gases, which then react to atmospheric vapor to actually produce sulfuric acid, chloric acid, and fluoric acid. And all of those are, if we breathe those in too much quantity, then they are toxic for us. And you can get above the level of toxicity by in two ways: by the concentration of the gases in the fog or whatever it is, the cloud that is carrying those things, but also if you have a long-term exposure, even if it's a low concentration, but if you're breathing it for a very long time, then that can result also in that your body actually gets above toxic levels, and that's it can be life-threatening. Okay. So that's one aspect of it. Yeah. So the volcanic pollution, or the VOG, instead of fog.
Yeah. I love that word.
But the other thing is, especially in a bit more powerful sort of basaltic eruptions than we've seen here in the Reykjanes Peninsula, you will produce eruption columns that actually go fairly high in the atmosphere, so 9, 10, or even up to 15 kilometers, and even slightly higher than that.
Was that the case with Eyjafjallajökull?
Yes, well, it was actually quite weak eruption as well. Okay. So it had a lower, but if you go further back, like the Laki eruption, 1783, even Hvalur in 2014-15 had a very low plume, but it generated a significant pollution. But if they put enough of those gases out and high enough, so you put it into the upper troposphere, sort of at 9 kilometers, or even into the lower stratosphere up to 17 kilometers. Then it is actually will react with atmospheric vapor there and will form sulfuric acid droplets, which we call aerosols. And that is basically, it's quite often referred to as the dry fog, because it doesn't produce any dew. So if it comes even over the land, everything is still dry, it won't get wet. But anyway, so if it's up there, then actually it's thick enough that it actually will block incoming solar radiation. So you reduce the amount of solar radiation reaching the surface. So you'll have surface cooling. And so while the cloud is there, it can actually cause cool weather over the area that it covers. And like in the Laki eruption in 1783, it covered the whole northern hemisphere. And so it was cold in a lot of places in the northern hemisphere at the surface. What it does though up in the sky is that it absorbs solar energy. So that cloud, which is moving at, say for argument's sake, between 10 and 15 kilometers, it is moving along, is blocking the sun reaching the surface, reducing the amount of solar radiation to the surface, but it's absorbing up here. And because Iceland is a high latitude location, most of that cloud that you put up there actually covers the northern part of the northern hemisphere. It covers the polar region. And if you absorb energy into a cloud like that, you start to heat up that layer. And then you heat up the atmosphere at 10 kilometers high above the polar region. And that results in reducing the temperature gradient between the pole, North Pole, and the equator. That temperature gradient, the steeper it is, so the greater the temperature differences between the equator and the polar region, the stronger the westerly winds are, or the jet stream. And they stream, really fast. They come over us, and it makes them much more stable. Now, if you reduce that gradient, they could become weaker, and they start to meander. Instead of coming straight from the west to the east, they will actually go way up north, and then way down south, and way up north again, and that results in air masses actually moving, hot air masses going further north, cold air masses coming further south, and we start to get more extreme weather. And it also starts to stay with us longer. So instead of having the low pressure system go over and pass us in 2 days, it takes maybe 3 weeks. So in a simple term, it also affects the way the atmospheric currents flow. In other words, it will affect the climate.
But taking from this eruption did not have enough power?
No, it did not. It did not go high enough. Not enough sulfur coming out. Its volume is so. In order to have a sort of at least sort of a hemispheric impact, you need an eruption on the scale of Laki. Then we're talking about 1 million ton of SO2 per day. Instead of 2,000.
That's like a different scale.
Yes, the order of magnitude, several orders of magnitude difference in terms of the amount of, and you also have to convert that SO2 into H2SO4 aerosol droplets, or you have to change it into sulfuric acid droplets.
There are often these comments from a little bit like climate change conspiracists that are like, I'm not driving my car here, but there we have the volcano going off and polluting a lot of, the air with CO2. Just from the basis of CO2 levels, do these eruptions have a significant impact?
None whatsoever. It's so the amount of CO2 that comes out in these eruptions is so small compared to the CO2 levels of the atmosphere. Even the big eruptions don't have any impact on the CO2 budget of the atmosphere. But another very important element of volcanic eruptions in this regard is that our atmosphere is not something that is glued to Earth. So we are always losing some of the atmospheric molecules into space.
Mm-hmm.
And if we wouldn't have volcanic eruption, which actually put all the gases out, well, they put out the gases they put out when they erupt, then we wouldn't have atmosphere because we would lose it and it would be gone a long time ago.
Yeah.
Because the volcanic eruptions, they replenish the atmosphere.
Mm-hmm.
They bring water from, for example, from deep within the earth
Mm-hmm.
to the surface. And that helps maintaining the oceans and our atmosphere. And best sort of estimate is that there is equivalent of, in terms of water, in the mantle, so that several thousand kilometers depth, there's equivalent of 7 oceans.
Wow.
Stored there. Which is good for us because
yeah.
that means that we get a lot of spare water.
Yeah. That's immense. Okay. That's mind-blowing, actually.
It kind of is. And
yeah.
you see, life on Earth would not be here without volcanoes, would not be here without plate tectonics.
Mm-hmm.
So plate tectonics, they generate the plate boundaries, which have all the earthquakes and all the volcanoes.
Mm-hmm.
And that can be hazardous to us.
Mm-hmm.
But at the same time, what is hazardous to us actually provides the essence of life.
Mm-hmm. So you can't just take, you always need to...
No, it gives and takes.
Yeah, yeah.
And so we have to, well, the best thing we do really, probably should never say you have to do this or have to do that,
Mm-hmm.
but the best thing we would do is to learn to live with those things and be prepared for them so we can minimize their impact on our everyday
Mm-hmm.
life.
Thank you so much for your time.
You're welcome.
Yeah, I really appreciate it. And I think we talked about so many very interesting topics and so much information now. Yeah.
Yeah, no, that's my pleasure.
Yeah, okay. Thank you for watching the second part of our interview with Þorvaldur. I hope you enjoyed, and I'm gonna see you back next week with another video. Bye.